All right, guys, working energy problem. Evan mows the grass by applying 225 newtons of force to the handle of the lawnmower. The handle makes a 60-degree angle with the ground. If he pushes the lawnmower for 500 meters, how much work is done? And this is talking about by Evan on the lawnmower. So if we go to another slide, sort of draw it out. Here's what we know. We know we've got this lawnmower. We know we're pushing on the lawnmower with a force down this handle of 225 newtons. We know the handle makes a 60-degree angle with the ground. And we move it for 500 meters. So we got a distance, or we'll say a delta x of 500 meters. We know that work is force times distance. So first of all, what force do we need to find? Yeah, the horizontal component of this. So we draw down a 90. We're going to solve for h. Remember, work is only done if the force is in the same direction as what? The motion. It's got to be in the same direction as the motion. So if we find h, we'll use cosine. Take cosine of 60 equals h over 225. Solve that out for h. Yeah, that's cosine of 60 is half. So it's 112.5. That's the force. So now just plug into force times distance. We're going to put 112.5 in for force. We're going to plug in 500 meters for distance.
56,250.
Yeah, we had 3 significant digits in our problem. The actual answer came out to be 56,250, and it's Newton meters or joules. But with significant digits, we would call that 56,300. So our correct answer with significant digits, oh, that's terrible, 56,300 joules. Everybody okay with that one? That one's just pretty much plug and chug. All right, here's our problem. We're using a set of pulleys. We've got an engine, 435 kilograms. Note that that's mass, not weight. We lifted a vertical distance of 3.5 meters. We're using a set of pulleys to lift it. So as this guy David is lifting it, he pulls 12 meters of rope. So he has to pull 12 meters of rope to lift the engine 3.5 meters. And we want to know how much effort force he applied if it's an ideal machine. Now remember, ideal machine means no weight, no friction. So let's work that part first, and then we'll come back and try the next part. All right, so here's what we know again. We know the mass of the engine, 435 kilograms. We know we're trying to lift that engine a distance of 3.5 meters. And we know that to do that, we have to pull out a distance of 12 meters of rope. We're trying to find the force that we have to apply to the rope to lift the engine. In an ideal machine, workout has to be equal to work in. So the workout is what we actually accomplish. We're moving this engine 3.5 meters. We know that workout is going to be force times distance, and work in is going to be force times distance. But the force for the workout is what force? What do we need to plug in for F for workout?
Weight.
The weight. That's what we're trying to move. So 435 times 9.8. So 4,263 is our force here. It's the weight of the engine. We move that engine a distance of 3.5 meters. So that's our work out. Force times distance. The work in, we're trying to solve for the force, the effort force. We know the distance, the effort distance, the amount of rope we have to pull is 12 meters. So all we're going to do now is divide both sides by 12 meters. Move it over here and solve out for F. So 4263 times 3.5 divided by 12. And with three significant digits, well, first of all, our force comes up to be 1,243 newtons. But with significant digits, that'd be 1,240. All right, that is what we call our effort force, 1,240 or 1,243 if we don't take into account significant digits. Now, I'm going to backtrack and look at the other part of the problem. Part B says if the actual force needed to lift the engine was 1,400 newtons, what was the work in? So remember, instead of an ideal machine, we're talking about a real machine this time. The work in is how hard we have to pull times what? How far we have to pull in this case, right? So in that problem, they told us that in the real world with friction, our effort force was how much? 1,400. So that's our effort force. Our effort distance is still the 12 meters of rope we have to pull out. So 1,400 times 12. We end up with 16,800. So that's the work in the real world, 16,800 Newton meters or joules. All right, and then the work out. Work out is what you're trying to accomplish. And we already had that set up over here. For the work out, weight times distance that weight is moved. So take the weight of the engine times the distance we moved it. So 4263 times 3.5. So our work out with the right significant digits was 14,900. And my marker is very off. But 14,900 joules is the work out. 14,900. That's not right. That can't be right, right? So let me recheck my math here. 42.
Your work in was 16,800.
Oh, I wrote it down wrong. Okay, wrote it down wrong. This should be 16,800. 14,900 would be correct. The work out's always got to be less than the work in the real world, right? And it is. 14,900 work out, 16,800 work in. Yes. Let me take a second.
So we just need to figure out the work in on that problem.
This is the same problem continued. Next, we want to know what's the mechanical advantage.
Mechanical advantage is all.
The mechanical advantage is a ratio of what to what?
Work in, work out.
Nope.
No, it's the. That's the resistance force and your.
Yeah, mechanical advantage is a ratio of your resistance force to your effort force, which in this problem is going to be, in this problem, our resistance force is our weight. So if we go back to our previous problem, our weight was what? 435 times 9.8, 4263. That's our resistance force. That's the weight of the thing we're trying to move. And the effort force is how hard we actually have to pull to do that. And how hard did the problem tell us we had to pull? 1,400 newtons. So our newtons cancel. 1463 divided by 1,400. That gives us a mechanical advantage of about 3.05. MA equals 3.05. Now, that doesn't have any units. What that means is that pulley seems to do what to our force? The force we pull on, what does the pulley do to it? It multiplies it 3.05 times. It makes our force go up. But the trade-off of our force going up is that what also has to go up? The distance we have to pull that. So there's a trade-off. All right, the next part of this problem is to calculate the ideal mechanical advantage. And what you got to remember is the ideal mechanical advantage does not take into account what? Doesn't take into account friction. It's a ratio of the, what distance?
Effort distance.
The effort distance
Effort distance.
divided by the resistance distance. And in this particular problem, the effort distance is how much rope do we have to pull, which was 12 meters. So 12 meters divided by the resistance distance is how far do you move what you actually were trying to move, which in this problem was 3.5. So 12 meters divided by 3.5, 3.43. And something you should see, the ideal mechanical advantage should always be higher than the regular mechanical advantage, because this one doesn't take into account friction. It has no unit. Friction lowers the efficiency of your machine, so the mechanical advantage is always less than the ideal mechanical advantage.
What's the most efficient thing?
All right, the next part, the percent efficiency. To calculate percent efficiency, pretty simple calculation to do. It is the ratio of work out divided by work in times 100. So if you look back to our previous problems, our workout was 14,900 joules. The work that we put into those pulleys was 16,800 joules. Times 100. So if we calculate that out, 14,900 divided by 16,800, we end up with 88.7% efficiency. And that's pretty good. That's real good for a machine. 88.7. Now, the next question was what is meant by mechanical advantage? And I sort of already explained that to you. It's basically how many times your machine does what? Multiplies your effort force. How many times a machine multiplies your effort force? And remember that mechanical advantage, MA, does take into account what? Your input force or your effort force. And it does take into account friction. And the very last question in this problem was how large was the frictional force? We're going to need to backtrack just a little bit here. All right, if you remember on part A, we calculated that if this was an ideal machine, we should have to pull with a force of 1,243 newtons. That was our answer to part A. If there was no friction, we ought to have to pull 1,243 newtons of force to lift this heavy engine. But then in part B, it told us in the real world, we actually had to pull that hard, 1,400 newtons. So how much friction is there? Subtract those two. And when we subtract them, that'd give us 157, right? So the frictional force, the force that is resisting our input force, 157 newtons of friction. And that is as hard as those problems get.